sliding window RMS is a technique used to calculate the RMS voltage of a signal within a defined window that continuously slides along the signal. For a signal xn, where n is the time index, and a window size n, the sliding window RMS at time t sub 0 is given by the formula RMS t sub 0 equals the square root of 1/n times the sum of xn squared, where n ranges from t sub 0 minus n plus 1 to t sub 0. To implement this, firstly, start with an empty window of size n. Secondly, as new samples of xn arrive, add them to the window and remove the oldest sample. Thirdly, calculate the RMS voltage using the formula at each time step. The sliding window RMS technique provides a time-varying estimate of the RMS voltage. It can be used for real-time detection and analysis of voltage sags. In terms of detection, the RMS voltage is compared to a predefined threshold. If the RMS voltage falls below the threshold, a voltage sag is detected. For classification, the duration and magnitude of the voltage sag can be classified using predefined criteria based on RMS voltage deviation. Regarding analysis, the sliding window RMS can provide insights into the characteristics of voltage sags, such as their impact on load equipment and their implications for power system operation. The window size n should be chosen based on the desired trade-off between time resolution and noise reduction. Sliding window RMS is often used in conjunction with other techniques for voltage sag detection and analysis, such as transient energy calculation and phase angle jump detection. Voltage sags are short-duration reductions in voltage magnitude. They can cause equipment malfunction and process interruptions. Monitoring voltage sags is crucial for maintaining power quality and ensuring reliable operation of electrical systems. RMS, or root mean square, voltage is a statistical measure of the magnitude of a varying voltage. It's effectively the direct current voltage that would dissipate the same amount of power in a resistor as the alternating current voltage over a complete cycle. Understanding RMS voltage is fundamental to understanding voltage sags and the role of sliding window RMS in their analysis. The sliding window RMS method provides a continuous assessment of the RMS voltage, capturing the dynamic changes that occur during voltage sags. The formula for sliding window RMS involves calculating the square root of the average of the squared values of the signal within the window. This is done for each position of the sliding window. The choice of the window size, n, is a critical parameter. A larger window size provides better noise reduction but reduces time resolution. A smaller window size improves time resolution but may be more susceptible to noise. Implementing the sliding window RMS involves managing a data window that holds the most recent n samples of the voltage signal. As each new sample arrives, it's added to the window, and the oldest sample is removed, maintaining a constant window size. This process allows for the continuous calculation of the RMS voltage as the window slides along the signal. The advantages of sliding window RMS include its ability to provide a real-time estimate of the RMS voltage and its suitability for detecting and analyzing voltage sags. Its real-time capability makes it valuable for applications where immediate detection and response to voltage sags are required. For voltage sag detection, the calculated RMS voltage is compared against a predefined threshold. This threshold represents the acceptable lower limit of the voltage. When the RMS voltage falls below this threshold, a voltage sag is detected. The depth and duration of the sag are then analyzed to classify its severity. Classification of voltage sags involves categorizing them based on their depth, which is the percentage reduction in voltage, and their duration, which is the length of time the voltage remains below the threshold. Standards like IEC 61000-4-30 define specific criteria for classifying voltage sags. Analysis of voltage sags using sliding window RMS helps understand their impact on equipment and power system operation. This analysis can reveal the causes of voltage sags, predict their effects on sensitive equipment, and develop mitigation strategies to improve power system resilience. Voltage sags can originate from various sources, including faults in the power system, starting of large motors, and switching of heavy loads. Identifying the source of a voltage sag is essential for implementing effective mitigation measures. Mitigation techniques include installing uninterruptible power supplies for critical loads, using static VAR compensators to improve voltage stability, and upgrading power system infrastructure to reduce fault currents. The choice of window size in the sliding window RMS calculation affects the accuracy and responsiveness of the sag detection. A smaller window size allows for faster detection of voltage sags but may be more susceptible to noise and transient disturbances. A larger window size provides better noise immunity but may delay the detection of short-duration voltage sags. Choosing the appropriate window size requires a trade-off between these two factors, depending on the specific application and the characteristics of the power system. The sliding window RMS method can be combined with other signal processing techniques to improve the accuracy and reliability of voltage sag detection and analysis. One such technique is wavelet transform, which can decompose the voltage signal into different frequency components, allowing for the identification of transient disturbances and noise. Another technique is the S-transform, which provides a time-frequency representation of the voltage signal, enabling the detection of sudden changes in voltage magnitude and frequency. Adaptive thresholding can also be used to improve the detection of voltage sags in noisy environments. Adaptive thresholding involves adjusting the detection threshold based on the background noise level, reducing the likelihood of false detections caused by noise. The implementation of sliding window RMS typically involves using digital signal processing techniques. The voltage signal is sampled and digitized using an analog-to-digital converter, and the sampled data is processed using a microcontroller or digital signal processor. The RMS voltage is calculated for each sliding window position and compared to the detection threshold. The results of the voltage sag detection and analysis can be displayed on a screen or transmitted to a remote monitoring system. The monitoring system can provide alerts when voltage sags occur and provide detailed information about their characteristics. The sliding window RMS method is widely used in various applications, including power quality monitoring, industrial automation, and protection systems. In power quality monitoring, it is used to continuously monitor the voltage and detect voltage sags that may affect the performance of sensitive equipment. In industrial automation, it is used to protect equipment from damage caused by voltage sags and to ensure the reliable operation of industrial processes. In protection systems, it is used to detect faults in the power system and to initiate protective actions, such as tripping circuit breakers. The accuracy of the sliding window RMS method depends on several factors, including the sampling rate of the voltage signal, the resolution of the analog-to-digital converter, and the accuracy of the RMS calculation algorithm. The sampling rate should be high enough to capture all the significant frequency components of the voltage signal. The resolution of the analog-to-digital converter should be high enough to provide sufficient accuracy in the digitized data. The RMS calculation algorithm should be accurate and efficient. The performance of the sliding window RMS method can be evaluated using various metrics, including the detection rate, the false detection rate, and the response time. The detection rate is the percentage of actual voltage sags that are correctly detected. False detection rate is the percentage of non-voltage sag events that are incorrectly detected as voltage sags. The response time is the time it takes for the method to detect a voltage sag after it occurs. In practice, the sliding window RMS method is often implemented using specialized hardware and software. There are many commercially available power quality monitors that incorporate the sliding window RMS method and other signal processing techniques. These monitors provide a comprehensive solution for monitoring power quality and detecting voltage sags. Open-source software libraries are also available that implement the sliding window RMS method. These libraries can be used to develop custom voltage sag detection and analysis systems. When using the sliding window RMS method, it is important to consider the limitations of the technique. The method is sensitive to noise and transient disturbances, and it may not be accurate in highly distorted voltage waveforms. It is also important to choose the appropriate window size and detection threshold for the specific application. The use of the sliding window RMS method in conjunction with other signal processing techniques can improve the accuracy and reliability of voltage sag detection and analysis. The sliding window RMS technique is a valuable tool for power quality monitoring and voltage sag analysis. Understanding its principles, implementation, and limitations is essential for using it effectively. It allows for continuous monitoring and capturing the dynamic changes during voltage sags which can impact a system. By carefully selecting the parameters and using appropriate signal processing techniques, the sliding window RMS method can provide accurate and reliable voltage sag detection and analysis. Voltage sag detection thresholds are often based on standards like SEMI F47 or ITIC curve, which define acceptable voltage tolerance levels for equipment. These standards specify the minimum voltage level and duration that equipment should be able to withstand without malfunctioning. The sliding window RMS is a common method used to detect deviations from these curves. Furthermore, understanding the frequency components of the voltage signal can help differentiate between voltage sags and other types of disturbances. Harmonics, for example, can distort the RMS voltage calculation if not properly filtered out. Therefore, pre-processing the voltage signal with appropriate filters is often necessary. In some applications, it is also important to consider the phase angle of the voltage signal. Phase angle jumps can indicate certain types of disturbances, such as capacitor switching or transformer energization. The sliding window RMS method can be combined with phase angle measurements to provide a more comprehensive assessment of power quality. Advanced techniques, such as machine learning, can also be used to improve the accuracy of voltage sag detection and classification. Machine learning algorithms can be trained to recognize different types of voltage sags based on their characteristics such as depth, duration, and shape. The sliding window RMS method can be used as a feature extraction technique for these algorithms. The sliding window RMS method is also used in microgrids and distributed generation systems to monitor the voltage at the point of common coupling. This ensures that the voltage remains within acceptable limits and that the distributed generation system does not adversely affect the power quality of the grid. In addition to voltage segs, the sliding window RMS method can also be used to detect voltage swells, which are short duration increases in voltage magnitude. Voltage swells can also damage equipment, and it is important to detect and mitigate them. The sliding window RMS provides a good way to see both. When implementing the sliding window RMS method in real time, it is important to optimize the code for performance. This may involve using efficient data structures such as circular buffers and optimizing the RMS calculation algorithm. The computational complexity of the sliding window RMS method is relatively low, making it suitable for implementation on embedded systems. However, the computational load can increase significantly for large window sizes or high sampling rates. In these cases, it may be necessary to use specialized hardware, such as field programmable gate arrays, to accelerate the computation. In summary, sliding window RMS is a powerful and versatile technique for voltage sag detection and analysis. Its simplicity, real-time capability, and adaptability make it a valuable tool for a wide range of applications. By understanding its principles, implementation, and limitations, electrical engineers and technicians can use it effectively to improve power quality and ensure the reliable operation of electrical systems. Finally, let's explore the formula's intricacies a bit more. The term xn2 inside the summation signifies squaring each voltage sample within the window. Squaring the voltage values makes all values positive, which is essential for accurately representing the energy content of the signal regardless of its polarity. This is because both positive and negative voltage values contribute to power dissipation. The summation xn2 n equals t sub 0 n plus 1 to t sub 0 calculates the sum of the squared voltage samples within the window. The limits of the summation n equals t sub 0 n plus 1 to t sub 0 define the range of samples included in the calculation. T sub 0 represents the current time index and n is the window size. Therefore, the summation includes the n most recent voltage samples. The term 1/n calculates the average of the squared voltage samples within the window. Dividing the sum of squared values by the number of samples provides a measure of the average energy content of the signal within the window. Finally, the term sqrt calculates the square root of the average squared voltage. Taking the square root converts the average squared voltage back to a voltage value, which represents the RMS voltage. The RMS voltage is a measure of the effective voltage of the signal, which is related to its ability to deliver power. In the implementation phase, the start with an empty window size n ensures a clean slate before the calculation begins. This prevents any previous data from influencing the current RMS value. As new samples arrive, the addition of new samples ensures that the window always contains the most recent voltage data. This is crucial for capturing the dynamic changes in the voltage signal. The removal of the oldest sample maintains a constant window size. This ensures that the RMS calculation is always based on the same number of samples, regardless of the time. By understanding the intricacies of the sliding window RMS formula and implementation, we can effectively use this technique for voltage sag detection, classification, and analysis. The sliding window RMS can provide insights into the characteristics of voltage sags, such as their impact on load equipment and their implications for power system operation. In conclusion, it stands as a vital asset in power quality management, offering a clear view of voltage fluctuations and aiding in the protection of sensitive electrical equipment.